We want to now talk about energy considerations for electricity. If we have a situation such as we see over here where we have a large positive charge and a couple of negative charges, and then we pull the negative charges away, we know that those negative charges are going to be attracted to the positive charge, which means that while we're adding work to the system, exerting a force through a distance, the electric field is exerting a force opposite the motion and doing negative work. Because electric field is a conservative force, it turns out that that negative work will be stored up in the form of potential energy. So we will have electrical potential energy when we move charges around like this. Now, if one of these charges is big enough, and we treat the others, or one of the others, as a test charge, then we can define a concept known as electric potential or voltage. So let's look at that. Before, we talked about electric field and forces. We know that in mechanics we had forces, units newtons, and in electrostatics and electric current we've got electric field, which is newtons per coulomb. And this worked well if we had a small charge that was exploring the forces that it experienced due to many other source charges. Well, in the same way that in mechanics we had potential energy, when measured in joules, now we have electric potential, which is the potential energy per charge, and it has units of joules per coulomb, which have the special name volts. Probably a unit you've seen many times, either on batteries or in your house on electric appliances. Now, something I like to point out here, just like we had electric field, we've talked a lot about an analogy with gravitational field, where you'll remember that gravitational field was the force per unit mass measured in newtons per kilogram. Well, we could do something then for gravitational potential. Gravitational potential energy was mgh. Then we could talk about a gravitational potential, which would be potential energy per unit mass, which would just end up being gh. G is a constant. H tells us how much gravitational potential we have. So I like to think of voltage, electric potential, as being very tightly analogous with height. To extend this height analogy a little bit more, imagine you were a caveman living in ancient times, and you need to defend your little settlement. So you build your settlement at the top of a hill. This way, when the other warring cavemen come up after you, they have to run up the hill. However, just being at the top of the hill with your settlement is not enough. This has a large gravitational potential, but before you have any energy, you need to stockpile some mass so that you can use that gravitational potential energy. So you stockpile a lot of rocks. And now, when the marauders come up to get you, you can just take the rocks and throw them down at them. And you have a tremendous advantage because all of these rocks have a much greater energy just due to the gravitational potential they're at. They're at an elevated height or more energy per unit mass. We can use the concept of electric potential or voltage to understand things such as the work done on a charge. Remember that the definition of potential energy originally was based on the work done. The change in potential energy is simply equal to minus the work done by a conservative force. In this case, electricity. So the work done by electricity in moving from point A to B is minus the change in potential energy, or minus UB minus UA, the final minus the initial. But then to turn that into a voltage, we simply divide it by the charge. We get the potential energy divided by the charge, but that's just the voltage at A, the electric potential at A, minus the electric potential at B. And we call that the voltage difference between A and B. It's the voltage at A minus the voltage at B. And if we go from A to B, then VAQ times VAB is the work done by the electric force in going from A to B, or it's the work done against the electric force if we move from B to A.